Today on This Old Tony, let's talk about angles stuff. Okay, fine, hold on a minute. The plan was to avoid using this word at all costs, but in this video, we're basically talking about trigonometry. Now wait, I know you hate that word. You've probably hated it since high school. I can't blame you. And that's why it was renamed shop math. Let's talk about sine bars, maybe sine tables, potentially angle blocks, why they work, and how you use them. We may get into cosine error, and if there's time, how to use all this math to take finer cuts on your lathe than you thought you could. All of this stuff, or all of the things I just mentioned, come down to trigonometry. I mean shop math. If you put my back to the wall, I'd tell you trigonometry is actually pretty cool. Totally worth giving it a second chance. And, my personal theory, they hit you with trigonometry right at that point in life where boys and girls start, well, maybe thinking about other stuff. And let's be fair, no subject in school is going to top that. So trigonometry takes the back seat. No, wait, in that case, the back seat would probably be occupied. It would take the front seat? Now I've gone and confused myself. Now I realize trigonometry is a big word. It's got a lot of letters. Maybe that's why shop math works so well. But that said, there'll be very little math here. I'll leave that part up to you. Anyone that might be allergic to numbers, well, no hard feelings if you want to skip this video. Let's start at the beginning. Trigonometry comes from two words. Trigon, who was a famous Targaryen mathematician and inventor of the trigon insert, and ometry. I have no idea what that means, but there's probably a good Irish joke in there. Alright, enough screwing around. Settle down now. Do you know what this is? It's a sine bar. Come on, I literally said that not 2 sentences. And this magical, indispensable piece of shop equipment, if you do your part, can set crazy precise angles. Machining isn't all square parts or round parts, you know. Sometimes there are angles. And I'm not talking about those out of square parts you usually make. I mean intentional angles. Precise intentional angles. Need to make or measure a surface to exactly, I don't know, 10.123 degrees? Well, this is your ticket. Use it on your surface plate, on your mill, surface grinder, lathe, backseat of your car, wherever and whenever you need to make or find an exact angle. I know what you're thinking. This old Tony, how does that chunk of metal do anything at all other than make me spend even more money I don't have? Well, I'll show you. If we put this down on a flat surface, imagine for a moment my bench is a flat surface, maybe like your surface plate. It doesn't do much of anything at all. It's a good paperweight at best. But once you put fresh batteries in it, if you stick something under one side, check out what happens. The top, magically, is not horizontal anymore. It's at an angle. You walked right into that. If instead you put something under one of the pins and the top isn't at an angle, if it looks like this, check your batteries. But of course, just whatever that random angle isn't very useful, is it? Heck, we could have cut an angle like that on the mill without the dumb sine bar. But here's the thing, with just a little bit of effort, and maybe a calculator, we can know what that angle is just by measuring how big or high that something is we stuck under one side. In this case, that's about 2 inches, or 50 millimeters, more or less, which can only mean one thing. The angle that this sine bar is now set to is exactly 23.578 degrees. All thanks to a little bit of shop math. The thing that really blows my mind is that those two things, the height and the angle, they're related. You can't change one without the other changing. How on earth does the sine bar know that the height changed? How does it convert it to an angle? And how does it do it so precisely? Well, I wouldn't be so bold as to claim to know the will of the gods, but what I can tell you is this, and don't panic, hopefully this should make more sense in a minute. The angle the sine bar makes with the table in this case is the inverse sine of the stack height divided by the length of the sine bar. In other words, the height of that stack is the length of the sine bar times the sine of that angle. I mean, technically those aren't other words, those are the same words, just said in a different order. And don't freak out, if sine or inverse sine, sometimes nicknamed arc sine, scare you, it shouldn't. Take a deep breath, let that high school trauma fade away, and you'll see they're right there on your calculator. It's a button just like any other button. Push it and the calculator will tell you the sine of whatever number you entered. Put in 30, push the sine button, and the calculator will tell you it's 0.5. And fun fact, the shift key on your calculator isn't just for typing capital numbers. Push the shift key, or the second function key in my case, and the sine button becomes the arc sine button, the inverse sine. Put in 0.5 and ask for the inverse sine, you get 30 degrees back out of it. If you'd rather not put your life in the hands of a calculator, you can also find these numbers in the back of the machinery's handbook, or probably any old high school math book. I guess I lied, it's not in the back, it's somewhere up near the front, but if you still trust me, have a look. The sine of 30 degrees is 0.5, just like the calculator said. Since we're here, and we're both just sitting around doing nothing waiting for the next really cool This Old Tony video, and to distinguish this a bit from other sine bar videos, let's have a very quick look at exactly what sine and cosine means, since I'll probably be dropping those words the rest of this video. That, and with any luck, we'll drive home the sine bar equations we just saw, so you're not just taking my word for it. You're not just trying to memorize something. Somewhere about 3,000 or 4,000 years ago, people were dying left and right from their ladders slipping away out from underneath them. Those were brutal times. To solve the killer ladder problem and ensure the survival of the human race, they invented trigonometry. Coincidentally, that's where the whole bad luck from walking under a ladder comes from. Check this out. This sine bar has two pins attached to it that are a very specific distance apart. The distance between those pins is exactly 5 inches. In theory anyway, depends on the quality of the sine bar you buy or you make. So does this sine table. The pins on this table are also 5 inches apart. We'll talk about why that's 5 a little bit later, but for now, these two things are exactly the same, except one of them is bigger. Can you guess which one is? But let's just look at the sine bar. Sine table is exactly the same thing. If we keep one pin still and only stack stuff under the other pin, the whole bar table moves in a circle with a radius equal to the distance between those pins, like a compass, right? When you're drawing a circle. And the higher we raise it, the larger the angle gets. Let's now take my fake flashlight and shine it at the sine bar, or sine table, or life-ending ladder, whatever. Note that I'm shining the light in from behind the angle of interest, in this case along the length of the bench it's sitting on. Because of that light, imagine for a moment our sine bar casts a perfect shadow. Now this isn't a perfect example because our sine bar has some thickness to it, so imagine just the top surface, that line, is casting the shadow. That shadow it's casting, the length of that shadow, is related to the angle. The steeper I make the bar, the longer the shadow gets. Now, there's a relationship there, and the relationship between the angle of that line and the length of that shadow it makes was given a funny name, sine. The length of that shadow is the sine of that angle. Now if I shine that flashlight down from the top, 90 degrees to what we were doing before, I get another shadow, this time next to the angle instead of opposite the angle. Since they were evidently running out of names back then, that shadow is called the cosine. So as we change the stack height, as that bar moves up and down through whatever angle, the length of both of those shadows changes. Now since our bar isn't changing length, hopefully it's apparent that the length of those two shadows are related. If the sine shadow gets longer, the cosine shadow has to get shorter, and vice versa. Now since there wasn't all that much to do 3,000 years ago, and most of their friends died slipping on ladders, they had plenty of time to give that relationship its own name too. In any given position of our sine bar or ladder, the length of the sine shadow divided by the length of the cosine shadow, they decided to call the tangent. And that's exactly what this is, a tangent. So let's get back to sines and cosines. Probably doesn't take too much imagination to see that there's a special point I can rotate this bar to, such that the length of the sine shadow is the same length as the cosine shadow. Can you guess what angle? Yes, 45 degrees. At 45 degrees, the sine and the cosine are exactly the same. Let's check the book. This lists sine, cosine, and tangent all in the same line for any given angle. You could see at 45 degrees, the sine and the cosine is the same. And now we know why the tangent is 1. Since sine and cosine are the same, those two numbers divided by each other is 1. This is fun. Let's keep going. So you don't sound like an idiot when you're explaining this to your friends down at the bar. The shadows we've been talking about are usually called the projections. This is the projection of the height, and this is the projection of the length. While we're here, there's one last thing I'd like to reinforce. Sine and cosine depend on which angle you're talking about. In our case, we were talking about the angle between the table and the top of the sine bar. If you wanted to talk about this angle up here, you'd have to switch your projections. That angle's shadow, or projection, would now be down here, and that would be the sine. And its cosine would be over here. That is sometimes tricky to keep track of, so be careful. If you decide to start projecting yourself onto your triangles, just make sure you're doing it right. For the three of you that are still watching, there's one last thing we should talk about so these numbers actually make sense in the real world. Back when Trigon was trying to help everyone out with their ladders, there was one big problem he couldn't quite crack. Everyone's ladders and sine bars were different lengths. Trigon's calculators, slide rules, and tables didn't work for everyone. And tragically, even more people were dying now. Then it hit him. Yes, it was probably a ladder. He would assume everyone's ladder, sine bar, sine table, giant Christmas tree, lookout tower, cable car wire, whatever. He would assume they were all one long, just one unit. Doesn't matter what, 1 inch, 1 foot, 1 meter, 1 mile. If everybody agreed on one, the sine and the cosine could work. Let's see how that works for our 5-inch sine bar. Since our actual sine bar is 5 times longer than the one that Trigon got all hung up over, now we have to multiply by 5. If we wanted to construct, say, a perfect 30-degree angle using a 5-inch sine bar, just like before, we need to figure out the stack height. So stack height is the sine of 30 degrees, which we saw is 0.5, times the length of the bar, times 5 inches. 0.5 times 5 is 2.5. Since we're working in inches, that's a 2.5 inch stack height. If our sine bar was 5 millimeters, that would be a 2.5 millimeter stack height. If it was 5 miles, that would be a 2.5 mile stack height. So now that we've packed 5 years of math classes in 5 minutes, let's talk about what you might stuff under your sine bar. Now, although for the stack you could technically use anything you wanted, usually, and especially when you don't want to get fired, you'd build the stack up with gauge blocks. This is a set of precision gauge blocks, or it used to be anyway. Now they're more like my fabrication blocks. But anyway, you pile these up like Legos to get to the dimension you need. For our 30-degree example on the 5-inch sine bar, we need to build up a 2.5-inch stack. So I'd grab the 2-inch block and the 1/2-inch block. The 1/2-inch block. Make sure your surface plate is meticulously clean. Get the blocks that you need, clean them, ring them together. Mine don't really ring anymore. And set up your sine bar. Now, of course, you don't need to use a 2-inch block and a 1/2-inch block. You could use 2 1-inch blocks and a 1/2-inch block, 5 1/2-inch blocks, 25 1/10-inch blocks. Machining knows no creative limits, as long, of course, your stack is the right height to get you the angle that you're hoping to work with. Now, you take the part that you want to inspect, something that has a 30-degree angle, like this 30-degree angle block. This is out of an angle block set. These are really handy to have, not that expensive. Not as expensive anyway as the gauge block set you'll need to go with your sine bar. But whatever you got, you put the part on the sine bar, and now we can come in with an indicator. This is a tenths indicator. Each division there is, I guess, 2.5 microns. I'm just going to zero it out, and then sweep the leg. Sweep the surface. Frankly, I expected that to be worse, given how I just threw everything out here on my surface plate. But that's reading 1/2 of a 1/10 of a 1,000th of an inch, aka 1/2 a tenth. That would be 1.25 microns. Now, of course, it depends on what you're measuring, but it often helps to build your sine bar fortress up against an angle plate of some kind. And usually, the back of your surface gauge will have pins that you can deploy. They'll stick out the bottom. Now, it's hard for me to show you, but you can use that to ride along the edge of your surface plate. And that way you can be sure everything is nice and straight. You're doing a nice clean sweep across the surface. You don't want your stuff falling over or introducing weird compound angles that could give you errors in your reading. Now, working with a sine bar to actually do machining is in principle the same exact thing. You'd set up your stack horizontally or vertically, however you need to get the work into the position to make your cut. That sometimes is easier said than done. Take this 5-inch sine bar, for example, on my mill. There's really no way to get it in the vise. It's just too big. This worked well when I had the Bridgeport, had a larger vise, but in this smaller vise, the sine bar is just too big. I could potentially use a parallel in the bottom of the vise, but it doesn't take very much to get out of the clamping range of these jaws. I could clamp onto the sine bar, and there's really not much room left for my work. If you imagine that on a parallel, with some angle to it, I just couldn't clamp the work. Ideally, I guess I'd be using a smaller sine bar here. Now, similar to what we saw on the surface plate, I'd probably set something like this up on an angle plate. I could clamp the angle plate down, then clamp the sine bar and the work to the angle plate. There is, of course, a limit to how big the work can be, so your setup would likely change a bit. Now, in practice, most of the time I can work with this little angle block set. Not as flexible as the sine bar, but I can mix and match these to get, the more popular angles, and they're much smaller, more compact. In this case, fit nicely in this vise. For bigger work, I've taken to using the sine table, though I bought that mostly to work on the surface grinder. Again, the function is exactly the same. The only difference is this has sort of this subplate. One pin is hinged at the front, and there's a pin at the back you can build the gauge blocks under. Then just lock down all the screws and attach your work to the top. If and when you go shopping for sine bars, you'll find that one of the most popular sizes is 10-inch, twice the size of this one. I'm not totally sure why, but I'm willing to bet it's because 10 is an easy number to multiply by. Any answer you get on your calculator calculator is a lot easier to multiply by 10 than, say, 9. This perhaps was in the land before calculators. But practically, the sine bar can be any size at all, though the longer it is, the more precise it usually is. And of course, you should match it to the size of your work. You wouldn't want to use a 1-inch sine bar to set up a 24-inch block of material on your mill. After 10, you'll find a lot of 5-inch bars like this one, and smaller 2.5-inch bars. Again, I think the idea used to be you multiplied by 10, because that was easy, then divided by 2 in the case of the 5-inch bar, or divided by 4 for the 2.5-inch bar. On top of that, I think most like mechanical trades books, manuals, that sort of thing, already list sine tables based on bar length. It's been a while, but I think I've seen those. Before buying mine, I actually made one of my own. I don't remember exactly what I needed this for, but I made it wider than your usual sine bar. I did my best to set these pins 5 inches apart, but they're brazed in place and they moved a little bit. To figure out that center distance, I just put a reference angle on the top and built a stack until the indicator sweep over that read 0 from one side to the other. Very similar to that 30-degree angle block we saw a minute ago, except I have a small granite standard. When that indicator sweep read 0, I could just do the math backwards. I knew the angle, I could measure the stack height, and it turns out the distance between centers on this is 5.020. Then I just stamp that into the bottom and use that number anytime I use this sine bar. One last thing before we wrap up the sine bar topic. You'll often hear that sine bars are only good to about 45 degrees. That's not really true. If I were to venture a guess, that may be rooted in the fact that most sine tables in the back of old machining books only went to 45 degrees. Now they only went that far, I believe, to save on printing. Anything over 45 degrees, and people used to know how to do the math. If you needed to know the sine of 60, for example, and your chart only went to 45, well, you knew that the cosine of 30 was the same value. So you'd find it that way. Though there is an upper practical limit to the sine bar, and that's about 60 degrees. In fact, on most sine bars, if you try to go above 60, you'll run into the actual body of the bar, down around here, below the pin. I haven't measured this, but that looks like it's pretty close to 60. The real reason goes back to the fact that the sine bar, as you lift it, traces out a circle. You remember this bit? Down in the lower range, up to about 15, maybe 20 degrees, sine bars can be crazy precise because the change is almost linear. Double the stack height and you almost double the angle. But as you wrap up around the circle, you're getting less bang for your stacking buck. As you approach 60 and beyond, the curve of the circle starts to flatten out a lot. Very small changes in stack height up there can result in big angle changes. My lathe is smarter than me. It's way better at math, which admittedly might not be saying much. But it doesn't need a pencil, it doesn't need a calculator, and is never wrong. Never. This is the Crossfeed. This handle pushes the tool in or out. I wind the handle in to take deeper and deeper cuts, making my parts smaller and smaller until they're scrap. That's how I know I'm done. Now the lathe has graduated dials, in this case in inches, to give me a better shot at making my parts the size I want. Now, lathes are made with one of two types of dial, direct read and indirect read. Direct read means whatever you dial in on the hand wheel is how much smaller the diameter of the work gets. To state the oblivious, lathes make round parts, and 9 times out of 10 you're interested in the finished diameter, not necessarily how much your tool moved. So on a direct read lathe, the hand wheel graduations and the diameter of the work are directly related. Move one whatever on the hand wheel, and your diameter would end up being one whatever smaller. This lathe happens to be indirect reading. I think all Colchesters are, but I can't be certain. The dials don't tell me what the diameter of the work is doing. They tell me how far the tool is moving. If I move the hand wheel, say 20 thou, you can see the tool post moves 20 thou. So in this case, we're reading the radius, and the diameter of the work gets 2 times smaller than what I dialed in. Neither is really better or worse, just different. Though it does stink when you're used to one type and you have to move to a different type. Taking a closer look at my graduations, we see that the smallest division is 1/1000th of an inch. So if I move the tool 1 thou in, I'm cutting 1 thou on the radius, and the work gets 2 thou smaller. Say now I'm almost done with my part, really close to done. And all I have left to do is to remove 1 thou on the diameter, and then, well, what do I do now on my dials? I'd have to do my best to split those divisions by eye. But how do I know that's 1/2 thou? What if it's 4/10 or 6/10? Well, for one, you could use an indicator, set up just like this one, and not trust the dials at all. But that's still a really small move on a hand wheel. That and taking a 1 thou cut or 0.025 millimeter, isn't as easy as it sounds. We're in the quantum realm here. Spooky stuff can happen, but that's a topic for another video. Instead, let's see if a little math can't save the day. This here is the top slide, or the compound. It goes by a lot of names, and by a lot, I mean 2. It's set 90 degrees to the cross slide, so that means no amount of turning this hand wheel will reduce the diameter of the part. Of course, if I turn my top slide to 90 degrees, then it works just like my cross slide, and I have the same problem. 1 division results in 2 thou diameter change, and I'm right back where I started. But check out what happens if I set my top slide to, say, 30 degrees. The scale reads 60, that's just how my lathe is laid out. But in this case, that 60 means 30 degrees off of 90, like 30 degrees off of parallel from the lathe axis. We've got ourselves a nice little triangle, with the motion of the top slide now 30 degrees to the axis of the lathe. If I wind the top slide in now, say a full turn, 100 thou, the cutting tool moves 86 thou in towards the chuck, and only 50 thou in towards the work, towards the lathe's center line. It moved the tool half of what I dialed on the hand wheel. If you didn't see it coming, that's because the sine of 30 degrees is 0.5. So now set up at 30 degrees, if I move the dial 1 division, the tool only moves towards the work half of a division. I can now, more confidently anyway, dial in a cut that would peel 1 thou off the diameter. No guessing between lines. If I were to set my top slide to 15 degrees, the sine of 15 is pretty darn close to 0.25. So that's 4 times less than what I turned the hand wheel. Now, to get the same 1 thou off the diameter, I can move 2 full lines on the hand wheel, which is a ton easier to read than trying to split the divisions by eye. Dialing in 1 thou diameter reduction is a lot different than actually getting a 1 thou smaller part. Frankly, being able to do that is what separates the wheat from the chaff. Since, you know, separating boys from men is no longer politically correct. Anyway, that's it. That's how your lathe does trig shop math all on its own, with no stinking calculator. Hey, so while we're here, you could also use a sine bar to set up your top slide. By eye, it looks pretty close to the 30 degrees we set on the scale, but here you could run an indicator along your sine bar and tweak your top slide angle until that indicator reads 0. I've also heard of people setting sine bars up against either like a test bar in the chuck or the quill of the tailstock, then mounting an indicator in the tool post, I guess, and sweeping this until the angle is correct. Again, until you had 0 indicator reading. I've never done this, and frankly, I don't know how you would hold this in space to even pull that off, but in theory, I guess it's possible. I would just load an indicator in the tool post and just watch the indicator reading as you move the top slide. So if this is set to 30 degrees and you wind it in 100 thou, if your indicator tells you 50 thou, half of whatever you wound in, then your angle is dead on. If it tells you 49 or 51 thou, well, you've got some tweaking to do. All right, I'm super excited about this. I saved the best part for last. Cosine error. Okay, fine, it's kind of dull. I was going to skip it, but I mentioned it earlier in this video, and I wasn't able to edit it out like I could time traveling using shop math, so let's give this some lip service. Now, I'm not a big fan of the term cosine error. It's not the cosine's fault, it's your fault. Come on, own up to it like a real wheat from the chaff. Cosine error is the error you can get from not aligning your measuring tool with the actual dimension you plan on measuring. Maybe it sounds obvious enough when stated like that, but usually it sneaks in more with test indicators than it does with dial indicators. But the concept is the same, and it's easier to demonstrate with a dial indicator, so we'll use this. It's actually a lot easier to demonstrate with a tape measure, but that'll just confuse everyone even more. Say we're trying to measure the height of this block. You'd be doing this on a surface plate, of course. Don't let anybody see you do this on a welding bench. If we're trying to measure the height of the block, it means we want to know this dimension. Of course, it doesn't have to be height. Maybe you're trying to measure run out, whatever, it's not important. But we have some dimension that we're interested in measuring, and in this case, we're using a dial indicator. Now, a dial indicator measures how far its stem moves, in line with the stem, right? If we put the indicator nice and straight, perpendicular to the top surface, we get a good measurement. But if we're not paying attention, didn't get enough sleep, or you got the whole shop heckling you for that karaoke bit you tried to pull off the night before, you might end up setting the indicator a little crooked. I mean, come on, it's not that much. What's the big deal? Say it's off 10 degrees for argument's sake. That'd be a lot, but let's say 10 degrees. To your bleary eyes, it looks good enough. Well, now you're no longer reading the height of the block. You're reading this line, this crooked line. Moral of the story, keep your indicator perpendicular to the dimension you're trying to measure. This is a 4-inch block of aluminum in the long dimension. If you measured it like a normal person, it says 4 inches. But if you insist on measuring it like a knucklehead, it's a 4¼ inch block. This is cosine error. The rule is reading 1 over the cosine of whatever that knucklehead angle is you're trying to measure the width of the block at. My apologies, I didn't mean to insult anyone's intelligence with those last two examples, but I wanted to convey just exactly what cosine error is. Earlier I said this comes up more with test indicators, because most people are pretty good at using dial indicators or a tape measure the way they were meant to be used. But you know, there are all types out. Test indicator by nature turns an angle into a straight measurement. You move the arm a few degrees, but it tells you inches or millimeter. It's not giving you an angular measurement there. It's not reading out degrees. So here, cosine error can be a little bit trickier. It can sneak up on you. You have to know how this thing is meant to be used, how the manufacturer designed it to be used, well, so you know what direction it's measuring in. Now, every test indicator is different, so read the manual for yours. For interrapids like this one, they're designed to read properly when the stylus is about 12 degrees, I think, to the work. If you lay it flat, you're not going to get a real number on the dial. If for some reason you do have to lay it flat, or that close to the surface, maybe you're trying to get inside a tight spot, you'll have to add the cosine error for 12 degrees in the case of the interrapid. And of course, if for some reason you change the stylus on the end, if you use a longer one or a shorter one, well, you have to accommodate for that too. Usually they come with, or you can find little charts and tables to help you out. Now, this is pure speculation. I've never really cared much to look into it, but I'd guess that's 12 degrees, because 12 degrees is how much you need to clear the sort of that knuckle or the hinge in the back of the indicator. You can sweep an entire part, get accurate readings, and not run into anything, like you could if you held it flat. Also, that 12 degrees isn't super critical. You know, if it's 10, if it's 14, if you're close, it's probably going to be good enough. That said though, test indicators like this are usually used to compare things, not to take a direct real measurement. Though of course you could if you took into account how it was designed. Maybe you're trying to use this to center work in a 4-jaw chuck, or center your mill over some existing bore or feature. You might not really care what the dimensions are there, just don't want the reading to change, or not very much anyway. Well, that's it, I think. That concludes our breathtaking, spine-tingling, awe-inspiring deep dive into the world of trig and shop math. Thanks for watching.